As we continue in Chapter 6, we're going to talk now about specific heats, heat capacity, and calorimetry. Calorimetry is one of the tools most often used by chemists to discover the energy contained within compounds, and more broadly within a mixture of compounds, especially in the food industry. But before we talk about calorimetry, we have to talk about heat capacity and specific heat capacity. Specific heat and heat capacity are terms that are definitely related to each other and sometimes used interchangeably, but we need to make sure we know the difference between them. Specific heat has the symbol S, and what specific heat is the amount of heat. We're going to use the symbol lowercase q for heat. That's a Q. The amount of heat necessary to increase the temperature of 1 gram of a substance by 1 degree C. Okay. How much heat is necessary to increase the temperature of 1 gram of a substance by 1 degree C? Over here on our table, you see some specific heats for various substances. Water is here. Water is 4.184 joules per gram degree C. You can tell that's the highest on this list. Water has a very high specific heat. When we talk about heat capacity, this is given the symbol capital C, and this is definitely related to specific heat, but it's the amount of heat necessary to increase the temperature of a given amount, a given mass. We'll use M for that, of a substance by 1 degree C. This isn't that different. Instead of 1 gram, it's however many grams we have, right? And so they're not that different, but they are related. The benefit of using a heat capacity is, say we're dealing with the same object over and over and over again. I don't want to have to always multiply the mass of that object by the specific heat for that material. I just want to multiply by a single number. So if I know the heat capacity of that object, then I can multiply by that heat capacity. And so the heat capacity C is equal to the mass of an object times the specific heat of that object. Right? And so instead of joules per gram degree C, we end up with joules per degree C. The amount of heat necessary, joules, to increase the temperature by 1 degree C. So we have our equation here that relates the mass of an object and the specific heat capacity. Let's tie all of this back to heat, Q. Q is equal to how much we have, M, times how much energy it takes to change that mass by 1 degree C, which is S, our specific heat, times how many degrees C we're changing it. That's the change in temperature. We're going to represent that as delta T. So Q equals ms delta T. This is a key equation for Chapter 6, and one that we'll come back to a good bit. We can also see this as Q equals, well, if M times S is equal to C, we can think about this as C delta T. Okay? as always, when we talk about temperature, delta T is equal to T final minus T initial. Right? How did those temperatures change? Let's use this set of equations real quick. We'll do an example here. We have some water heated from 8.5 degrees Celsius to 74.6 degrees Celsius. Calculate how much heat is absorbed in kilojoules by the water. And so our equation Q equals ms delta T. Calculate the heat. So we're solving for Q, which means we need to know ms and delta T. Our mass is given 466 grams of water. Our specific heat for water was on the previous slide, 4.184 joules per gram degree C. And then we need to calculate our delta T, right? It's the final temperature, 74.6 degrees C, minus the initial temperature, 8.5 degrees C. So we do all of that, and we get Q is equal to 1.29 times 10 to the 5th joules. It doesn't ask for it in joules. It specifies kilojoules. So we need to go ahead and convert that to kilojoules. 1 kilojoule is 1,000 joules. So we end up with 129 kilojoules. Okay? Keep an eye out. If it asks for it in a particular unit, make sure you give it in that unit. And if you're having difficulty with your conversion factors, go back to chapter 2 and learn those. All right. So in calorimetry, what we're doing is we're trying to use this idea that the energy transferred out of one object is absorbed by another object or by the surroundings. And so we perform a reaction inside a chamber, and within that chamber, the surroundings change temperature, and that's what we actually measure. And so in this calorimeter, this is a simple one that we would have done in lab if we were together in person. We just have a couple of styrofoam cups, a couple of coffee cups here, nested in each other to provide a little bit more insulation. We have a thermometer so we can measure the temperature. And within these cups, some reaction is taking place. And we use the thermometer not to measure the temperature of the reaction, but to measure the temperature of the water. In this case, the water of the surroundings. We use the information about the water to tell us something about the system, something about the reaction. And so, overall, the system is the whole thing. The system is the whole calorimeter, plus the water, plus the reaction, everything. So the system here is, this whole image is our system. Right? It's made up of 3 components: the water, the calorimeter, and the reaction. Right? Remember, Q is our symbol for heat. And so the heat that's exchanged in the system is equal to the heat of the water plus the heat of the calorimeter plus the heat of the reaction. Now our assumption is, and it's a pretty good assumption, is that the energy that's lost or gained by this whole setup is 0 for as long as the reaction is taking place. And if that's true, then we can switch the reaction to the other side. And we get Q reaction equals negative Q water plus Q cal. The water, we've seen this equation before, Q equals ms delta T. We've seen this equation before, Q equals C delta T for our calorimeter. Okay? Now it so happens that because we're doing this at constant pressure calorimetry, that the answer we get for Q reaction is equal to the enthalpy of that reaction. Okay? Again, this is the assumption we make, that in this setup, no heat enters or leaves. So let's say that we are adding a lead pellet. It has a mass of 26.47 grams at a given temperature. It's placed in a calorimeter with negligible heat capacity. So that is C cal is 0. And it has 100 milliliters of water. We're going to assume, knowing that the density of water is 1, that this is also 100 grams of water. Okay? It gives us the change here in water temperature, and it asks the question, what's the specific heat for lead? So S sub Pb for lead. So how does this set up? Well, Q reaction equals negative Q water plus Q cal, but I'm going to ignore that because it says that the heat capacity of the calorimeter is 0, therefore Q cal must also be 0. Since I'm not really doing a chemical reaction here, the heat on the left is really the heat that's lost by that lead pellet. And so I'm going to sort of write this out, expand this out. The mass of the lead pellet, I'm just going to read that Pb, times the specific heat of Pb, times the temperature change for Pb, is equal to negative, I can't forget that negative sign, the mass of the water, the specific heat of the water, and the temperature change for the water. Now this seems like a lot of pieces, but we know almost everything, right? It gives us the mass of the lead, 26.47 grams. We're asked to find the specific heat capacity for lead. The temperature of the lead, we'll come back to that one in just a second. Let me go ahead and write all the rest of this out. Can't forget that negative sign. The mass of the water, 100 grams. The specific heat of water was given earlier, 4.184 joules per gram degree C. And the temperature change for the water, 23.17 minus 22.50 degrees C. The thing that we have to sort of extrapolate here, based on the information given, is that if the lead pellet is dropped into the water, at the end of this whole process, the lead pellet and the water have to have the same temperature. Again, at the end of the process, that final temperature for the lead has to be equal to the final temperature of the water because they're together. The lead is inside the water. And so they have to have the same final temperature. 23.17 here is my TF, my final temperature for the lead. But I started at 89.98 degrees C. All right, well now, look, I have everything except this specific heat capacity. I plug everything into my calculator. On this side, I end up with negative 280.3 joules. This delta T here, if you've already started plugging things into your calculator, ends up being negative. And so our negative signs end up canceling out. We end up with a specific heat of lead that is 0.158 joules per gram degree C. Okay. Plug that in our calculator, we get a heat capacity for lead 0.158 joules per gram degree C. We're going to pause there, and then when we come back, we'll talk about how we calculate delta H for different reactions.